I hope everyone's doing well. I'm Mr. H. Thank you for joining me for this video where we are examining the parametric equations of a curve that develops for the trochoid. It's pronounced as trochoid with the CH having a K sound. There's a specific dimension you are looking here at. You have a center of a circle. If this circle were to roll along a straight line being the x-axis, this point P, which is a certain d units away from the center, there's a d units away from the center, it would trace a curve, and the curve can, depending on the dimension of d, look something like this. And it could vary in terms of appearance and form, but the general appearance of the trochoid would be something like that. If this dimension d, which is a certain number of units to this point P which traces, if d were equal to r, then the tracing would be more representative of a cycloid. Then the trochoid becomes a cycloid. But here in this particular video, we're looking and focusing on the particular fact that d should be less than the radius. The d, again, the distance from the center to that point P which traces, must be less than the radius for this video. When you focus here on this point P which is tracing, you know the point P, it will have a certain x and a y value. We have to determine that. These will be our parametric equations. And how will we go about doing that? We will do so by means of two representations. Representation number one, let's start with that. I am looking over here at this circle, and I have a center over here and I have a radius over here, and now I'm focusing on the radius. I'm extending this down. I have another radius. I have a certain angle here, theta. When you are looking at this with regards to your x and y axis, if you focus right here on this arc length right here, s is equal to r theta, and if you were to cut it and lay it down flat, it would be equal to the distance from this origin up to this point. Let's call this point A. From origin to point A, it would also be equal to your arc length, and that segment right here, I'm calling this a certain dimension x. I have a certain dimension y, which is this, the radius. From this center all the way to your x-axis, I have a radius, but it's also equal to y. And so I've developed two items. One is x, which is equal to your arc length, which is r theta, and one is y, which is equal to your radius. Again, remember this, for a circle that's rolling along a straight line over here, because it is in motion, if you were to cut off this arc length and lay it flat, it would be equal to, from this point up to this origin. You could lay it down and it would be equal to that. So the x value is equal to your arc length. Why is this important? Because it's going to feed in right over here. This x and this y are not synonymous with this. For differentiation purposes, let's make this double prime so we don't confuse the two. We've determined our x, we've determined our y using representation 1. Now let's focus on representation number 2. The focus of the first representation was on the complete radius. The focus of the second representation is now on this dimension d. I have a center, I'm looking a certain d units away, and I have a point here P. But the length of this segment here is d, because it's d units away from the center. I can take it across and take it up and generate a right triangle. I can take that right triangle and blow it up for you so you can see it better. Here's the center of the circle. Here's now a 90 degrees. Here's a certain angle theta, which would have been the same angle as this had you extended across. This angle theta is that angle theta. I have here d units, a hypotenuse. This right here is my point P, which is tracing the trochoid. And you know this dimension right here would continue all the way up to a certain radius. Now I'm looking at a certain x prime and a y prime, and I can use right triangle trigonometry to determine them. When I'm looking here at a sine theta, opposite of this is x prime. So I have x prime divided by the hypotenuse, which is d. You push it across. So now I see x prime is equal to d sine theta. When I'm looking here at this angle and I do the cosine of it, I have cosine theta is equal to a adjacent y prime over d, and you push this across and you know y prime here is equal to d cosine theta. When I'm looking from here to here, I have my x. When I'm looking from this point x value right over here, I'm looking here at an x prime. The difference of these two right here to right here will be equal to the x value of this point P. And that will be x double prime, and it will be exactly what will be showing you r theta minus d sine theta. When I'm looking from right here to here, I have my complete y dimension. Then when I'm looking from here to right over here, which you know was the right triangle we generated, I have my y prime. So y double prime is the difference of those two, which will give you the y value of your point P, and it will be equal to y r minus y prime d cosine theta. The parametric equation for the x value of your point P is r theta minus d sine theta. For the y value of your point P, it's r minus d cosine theta, and we're done. Before we close the video, keep in mind the difference of these two items, as you see right here, the x and x prime, y and y prime, represents the double prime values for your point P, but everything is always with relation to your origin. From the origin, you're looking here at this dimension, which will be your x double prime. From the origin, you're looking here at a certain y dimension, will be your y double prime, and these right here will be your parametric equations. And everything is always with relation to your origin. The difference of these dimensions gives you your relationship with regards to the origin. These parametric equations here will be correct. And our video comes to an end. Thank you for watching.